So good morning. Thank you for coming. So today also we have our hydrogen embrittlement mini symposium. This session is for the hydrogen mapping and novel critical experiment hydrogen material interaction part 2. Then this session we have 2 invited talks, and the total is the number of the presentation is 9. Then co-chairs, our name is Professor Dado Fani and Professor Jukik, and my name is Motomichi Koyama from Kyushu University. Now it's 11 o'clock on time. So first presenter is Professor Hiroyuki Toda. The presentation title is Assessment of Hydrogen Embrittlement via imaging techniques in high zinc, aluminum zinc, magnesium alloys. So please start when you're ready.
Thank you, Mr. Chairman. And my name is Toda. I'm from Kyushu University. I would like to thank the organizers of this symposium for giving me an opportunity to talk something here. Fundamentally, I would like to talk about the application of 3D imaging technique to the assessment of hydrogen embrittlement in high-strength aluminum alloys. As we have seen many times in this symposium, hydrogen are stored in various hydrogen trap sites. And different hydrogen trap sites have different binding energies. And if you take a look at this list, which is a list of binding energies for various hydrogen trap sites in aluminum, zinc, magnesium alloys, you can see that both screw and edge dislocations have relatively low binding energies, and grain boundaries, precipitates, and vacancies are intermediate. And atomic hydrogen adsorpted to aluminum surface and hydrogen separated from aluminum as a form of molecular hydrogen have very high binding energies. And by the way, we also observe hydrogen embrittlement in the case of aluminum alloys as a form of intergranular cracking and also transgranular quasi-cleavage cracking. And more recently, we have confirmed the existence of the other type of hydrogen embrittlement, which is the degradation of mechanical properties due to the existence of high-density hydrogen micropores. So we have the 3 mechanisms for hydrogen embrittlement of aluminum alloys. But if you take a look at the chart, then quasi-cleavage cracking might be associated with dislocations, and intergranular cracking is, of course, associated with hydrogen at grain boundaries. But as you can see, those 2 trap sites have fairly low binding energies with hydrogen. So at this moment, we can't correlate hydrogen embrittlement with hydrogen trapping in aluminum alloys. So this is the content of the present study. So we are going to apply the state-of-the-art 3D and 4D imaging technique to see what's happening inside in aluminum alloys. And also we have vigorously developed some image-based quantification techniques, such as 4-dimensional plastic slime mapping, crack driving force derivation along crack front line, and elemental and phase mapping techniques, crystallographic evaluation technique, and so on. So we are going to use some of those techniques to see the linkage between hydrogen embrittlement and hydrogen trapping. So fundamentally, we have used the simple projection type X-ray tomography in the high resolution 3D imaging beamline of the Japanese synchrotron radiation facility called Spring 8. So we have adjusted the experimental conditions to obtain a very high spatial resolution of about 1 micron, which is fairly close to the physical limit of this technique. And we mounted a specially designed tensile test rig onto the rotation stage of the tomography setup to make in situ observation of a tensile test, which is not so specialized one, and such as SSRT or something like that, because its strain rate is just 10⁻³ or something like that. And material tested was a aluminum zinc magnesium alloy with a zinc concentration of about 8.4%, which is fairly high compared to practical alloys of about 5.5% or something like that. In practical alloys, we should suppress, reduce zinc concentration below that level in order to avoid hydrogen embrittlement and stress corrosion cracking. In other words, we may be able to get very high strength materials if we overcome hydrogen embrittlement for this material. But anyway, hydrogen charging is performed to this material by simply applying the electrode discharge machining technique for sampling this specimen. According to a past paper, hydrogen concentration increased by more than 45% by simply applying EDM technique for sample preparation. So we are now looking at stress strain curves together with SEM micrographs. And fundamentally, we don't observe hydrogen embrittlement if you don't interrupt a tensile test. But if you interrupt a tensile test periodically in this way, to this extent, then we observe hydrogen embrittlement. So we are now superposing a series of 3D crack images onto this SEM micrograph. This is the initial crack. Actually, it is quasi-cleavage crack. And then it's propagated in this way fairly gradually with loading in this way. And in this case, about 30% of the fracture surface was covered by intergranular cracking and quasi-cleavage cracking. And if you increase the holding time from 5 to 45 minutes, then what happens is almost all entire fracture surface was covered by hydrogen embrittlement. Then strength and ductility is decreased drastically. So we would like to analyze the mechanisms of this hydrogen embrittlement behaviors by tracking particles. So we have a series of tomographic images, roughly 10 to 15. Then we can observe roughly 50 to 100,000 particles in the gauge section of a single specimen. Then we can track the physical displacement of all the particles by utilizing those morphological parameters. And we sometimes apply local pattern matching and trajectory prediction techniques. And we also apply the diffraction contrast tomography technique to see crystallographic structure of a material. But the problem is this technique is only applicable to the initial unloaded state. So we have crystallographic structure at initial unloaded state, which should be correlated with structure surface, because we have 30 to 50% plastic strain in between. In such a case, we use a 3D scattered data interpolation, and we don't go into the details of this technique this time, but fundamentally, we obtain local displacement field on the basis of the physical displacement of all the 100,000 particles. And what we do is we have a series of tomographic images, and then we extract the position coordinates of fracture surface patterns so that we can reproduce the configuration of fracture surface very accurately. Then we track the physical displacement of this fracture surface backward in time from fracture surface to the initial unloaded state to see the correlation between crystallographic structure and fracture surface. So we are now looking at reconstructed grain structure at the initial unloaded state. It has been reconstructed quite nicely in this way. And we are now looking at 3 initial cracks, hydrogen embrittlement cracks, which can be superposed onto the grain structure in this way. You can see quasi-cleavage crack here, and also intergranular crack here. If you take a look at this graph section, then you can see there is a crack, intergranular crack here, which matches quite well with the crystallographic texture of the unloaded state. Then this is intergranular cracks. We are looking at grain boundary energy as a function of grain angle with respect to the loading direction. And you can see that the initial crack has fairly high grain boundary energy, which is almost perpendicular to the loading axis, and then is propagated spreading through grain boundary planes with relatively high grain boundary energies. So this is a mechanism of intergranular crack. And this is transgranular crack. We are looking at SEM micrograph, and we can see quasi-cleavage crack here. And then we can find 7 facets on this quasi-cleavage crack. And then if you look carefully, we can find 14 very flat planes on the 7 facets of the quasi-cleavage crack. And we measured the crystallographic orientations of these flat planes and plotted on to the inverse pole here. And fortunately, the data points are widely distributed, and we couldn't find any association with crystallographic planes such as strip planes and cleavage planes or something like that. So it is fairly non-crystallographic. So we would like to further analyze the transgranular fracture behavior. In order to do so, we applied the 3D strain mapping technique. As I mentioned, we can track the physical displacement of all the visible particles throughout the deformation. Then we applied the Delaunay tessellation algorithm to generate space filling tetrahedra. And we can calculate local strain distribution on the basis of the physical displacement of particles via interpolation. So we are now looking at the 3-dimensional strain distribution with loading. This is applied strain level. And it is shown on the virtual cross-section. And this black lines is the section of a fracture surface, which was formed after this strain level. So we strained the specimen and then fractured at the end. So you can see that strain localization was observed even before the maximum load is applied. And also the initial strain localization was observed just after the elastic limit is reached. And then the quasi-cleavage crack was propagated through this intense shear band after the strain localization has been almost finished. So we would like to analyze this behavior in this way. We assume the hydrogen repartitioning occur during deformation. The crack is coming, and there is a crack tip area. And then hydrogen trap site densities, such as vacancies and dislocations, may increase during deformation. And also hydrogen comes in from the outside to the inside of the strain localized region. Although we don't take this hydrogen accumulate into account in this study, we are going to see this behavior by taking a look at in situ increase in trap site densities. So fundamentally, we do analysis by using these 3 equations. One is thermal equilibrium among various trap sites. And another is total hydrogen is partitioned to the lattice interstices and various trap sites, including micropores and nanovoids. And also, the surface energy of pore is reduced due to the existence of adsorbed hydrogen onto aluminum surface. And we fundamentally solve these equations utilizing these trapping binding energy data. And we also need some information about trap site densities. This is geometrically necessary dislocation and statistically stored dislocation. These can be directly measured from the 3D plastic strain distribution by taking a look at plastic strain gradient and equivalent plastic strain respectively. And we can also calculate vacancy concentration by assuming the motion of jogged screw dislocations during deformation. And in this case, we don't assume the annihilation of vacancies, because vacancies can be stabilized instantaneously due to the existence of hydrogen. So anyway, we can see very high SSD and vacancy concentrations, concentrations where strain is localized, and GN density is very high in the peripheral region. And this is 3D hydrogen concentration distribution during deformation. So we are looking at hydrogen concentration at the dislocation, hydrogen concentration at vacancy, and hydrogen concentration at micropore and nanoboids. And you can see that hydrogen concentration is fairly high for dislocations and vacancies in the strain localized regions. It is quite reasonable. But if you take a look at scale, it's 10 to 17, 10 to 24. So the level is fairly different. We have few hydrogen at dislocations. And you can see that outside the strain localized regions, hydrogen goes to micropores and nanoboids in this way. So this is the very last slide. We are looking at very localized hydrogen partitioning, repartitioning during deformation at a quasi-cleavage crack tip. So what we do is at the applied strain of 4.4%, we have a crack here. This is quasi-cleavage crack. And at the next rolling step, the crack is extended to this extent as a form of quasi-cleavage cracking. Then we identify the region of interest here and then calculate the partitioning of hydrogen in this localized region. So we have various hydrogen trap sites, and this is trapped hydrogen concentration, and this is hydrogen occupancy for each hydrogen trap site. And blue bars are the data after deformation of 4.4%. Red ones are no loading data. And at a glance, you can see that hydrogen concentration drastically increases at vacancies. This is due to the drastic increase in vacancy concentration. And probably the highest hydrogen concentration is observed at precipitates. So roughly 2/3 of all the hydrogen exists at age hardening precipitates, and the remaining 1/3 are distributed to the other trap site. And if you take a look at the dislocations, we have a fairly few hydrogen concentration at dislocations. If you take a look at the hydrogen occupancy, nanoboid and microboids, it is almost 100%. And then vacancy, intermetallic compound particles, and precipitates, it is roughly 1%. And then dislocations, it is just 1 ppm, which means we may be able to find just one hydrogen atom over 1 million possible trap sites. So it is significantly difficult to assume that quasi-cleavage cracking may be caused due to the existence of hydrogen at dislocations. So at this moment, we assume that this precipitates may be the potential source for quasi-cleavage cracking in the case of aluminum alloys. Okay, with that, I would like to summarize my talk. And strain localization was observed just after the elastic limit in this case, and crack initiation and propagation was subsequently observed where strain had been localized. And fairly gradual crack propagation was observed for both intergranular cracking and quasi-cleavage fracture, which are very different from the concept of brittle fracture. And if you hold holding time, we hold a applied displacement of a specimen, then we observe hydrogen embrittlement. And hydrogen embrittlement is associated with grain boundary energy in the case of intergranular cracking, but we don't know much about quasi-cleavage fracture at all at this moment. And in situ hydrogen partitioning was analyzed by measuring increase in vacancy concentration and dislocation density, and almost 2/3 of all the hydrogen would be accumulated at precipitates just before quasi-cleavage fracture. And fundamentally, the quasi-cleavage fracture of aluminum alloys was non-crystallographic. Thank you very much for your kind attention.
So, session is open for discussion, so please raise your hand, if any.
My question is, why hydrogen has a higher tendency to go to the vacancies when you have a higher plastic strain as compared to the vacancies? You mean vacancies? Like you showed in the last slide, it is probably the balance between topside density and binding energy. And in the case of dislocation, it's fairly low binding energy. And vacancies and nanovoids, we have a huge number of topsides and also relatively high binding energy. So that's why hydrogen goes to that side. So you're saying that the chances of coming out from the vacancies are... Sorry? The chances of coming out from the vacancies are less as compared to... I think gradually, very gradually, over years, or tens of years or something like that, due to the existence of oxide film onto the surface. Yeah.
So time is almost over, but a very short question? Okay.
Thank you very much.
So hydrogen embrittlement. Yeah. I think fundamentally, at least, for example, interfacial debonding of particles or something like that can be the trigger of hydrogen embrittlement in this case.
Sorry, time is running over. Let's thank speaker.